Alrighty, welcome back, mathematicians. We just covered 4.8, so now we're going to skip back to chapter 5, and we're on to section 5.3, all about the definite integral. So we saw in 4.8 the indefinite integral, and now we're moving on to definite. So the main difference between definite or indefinite and definite is that the definite integral has bounds on it. So we can see that we have a, which we're going to call the lower limit of our integration, and we have integral sign, and b, which is the upper limit of integration. So remember how in Riemann sums we talked about going from like t equals 0 to t equal 8, something like that? That's what we're doing now. We're not going to get a function back out, we're going to get a number back out. Hopefully. All right, so f of x is still our integrand, and x is our variable of integration. We can also write this limit, not this limit, the definite integral in terms of our Riemann sums and a limit of them, right? So we kind of talked about this last time, how it's going to be the limit as n approaches infinity. And then we have our Riemann sum, so the summation from 1 to n of f of a plus k times b minus a over n, which is just delta x. We write it that way so that we can have an n involved times delta x again, right? So that's kind of the connection from Riemann sums to the definite integral. All right. So the value of the definite integral depends on the function, not on the letter that we use to represent its independent variable. So we can have the derivative as f of x from a to b of f of x dx, the integral of f of u du, the integral of f of t dt. All the same function, just with different variables. All three of those are actually equal, making the variable of integration kind of what a dummy variable is, right? There's some Greek letters that I just really don't like to write, and so when they have them written somewhere, I like to put them in terms of x. Because we are getting a definite integral does give you a number as a result. It's going to give you the same answer each way. There's no x in your answers, there's no u, there's no t, no variables involved in our answer. We're going to get a number like 2 out. All right? So we talked a lot when we were first learning about derivatives of where is something differentiable, right? We know we can't take the derivative at a jump discontinuity. We can't take the derivative at a cusp or a corner, but can we take an antiderivative? Because, right, the antiderivative, I'm just trying to find the area under the curve. So I have this cute little curve here. I have a little jump right here, but I can find the area under all of these curves and corners. So this yields a theorem. Theorem 5.3.1, which is about integrability of continuous functions. So if a function f is continuous over the interval a, b, or if f has at most finitely many jump discontinuities, then the definite integral, so the integral from a to b of f of x dx exists, and f is what we say integrable. So if we go back and look at this picture I've drawn, we don't have a continuous function. So we're kind of in this or part. So when you have to make sure that we only have finitely many jump discontinuities. Remember, jump discontinuities, that's not when the limit of one goes up to infinity and one goes down to negative infinity like we see sometimes with tangent and secant. But jump discontinuity means I'm just going bump, bump, right? Like I am right here. So I only have one, that's a finite number. The difference between something that's a finitely many and infinitely many, in kind of the scope of knowledge that you all have and kind of the scope that the class is going over, it would be too much time to kind of explain the difference. But an example of something that has infinitely many jump infinitely many jump discontinuities is the function below. So f of x, that's equal to 1 if x is rational, so a number divided by another number, and 0 if x is irrational on the interval 0 to 1. So there's infinitely many numbers in between 0 and 1, and there's infinitely many rational numbers, and there's infinitely many irrational numbers between 0 and 1 as well. I know, crazy, infinity, but that's not what we're going to. That's just an example of something that has infinitely many jump discontinuities. All right, so properties of definite integrals. This is going to look a little similar to Riemann sum stuff, but most importantly, it's going to look similar to, hopefully, derivatives. The first two, maybe not so much. First two kind of similar to Riemann sums, and the rest of them will look a little similar from derivatives. So we now have f and g, and we're going to let them be integrable functions over our closed interval. So now we have our first property, which is order of integration. So basically saying that if I have the integral from a to b of f of x dx, if I switch those bounds, well, then I'm going to get the negative version of the integral. What that means is I'm taking, so that negative is going to stay there, and then from b to a, it's going to be that limit of the Riemann sums. Then goes to infinity, k equals 1 to n, f of a plus k, we'll just say times delta x right now, times, and I'm going from b to a, so I'm working my way back, so delta x is actually negative. So that's where that negative is coming from. All right. So just that integral alone is going to be the negative version, and then we make a negative because we want the original right there. All right. So now we have the zero with integral property. Basically, if my integral is from the same number to the same number, I'm going to be measuring the area of a line. Well, delta x in that case, would it be like a over a divided by a minus a divided by n? Well, that's just 0. So all of the Riemann rectangles are going to be of width 0. So that means our whole integral is going just to be 0. Basically saying that the area of a line is 0. All right, so now these kind of look a little similar to the next two, kind of what derivatives look like. So for coefficients, we're going to have that k times ab, the integral from a to b of f of x dx. And I also forgot my dx right here. Oh no. There we go. So basically we can pull that constant out and then do the definite integral. All right, sum and difference. I've kind of hinted at this before, this dx. The reason we have these parentheses here is that the dx is attached to both things. If we think about this like a sentence, like the capital letter sentence and dx is the period. All right, so I can then do the definite integral from a to b of f of x dx plus or minus the integral from a to b gx dx, right? So I can separate them, and their bounds will also be the same. So additivity is a really interesting one as well. So say we have the same integrand, f of x dx, in each integral, and one's going from a to b, and the other one's going from b to c. Well, we can see below that I'm just taking the area of the left plus the area of the right. Well, I can just take the area of the whole thing, and so we're going to combine the bounds, so we'll do the integral from a to c of f of x dx, right? So this only works if these two guys match. All right, so the next is the min and max inequality. So I've already drawn a picture of kind of what we're going to be talking about. So we're going to let capital M, or big M, be the maximum of f of x, and little m be the minimum of f of x on the interval a to b. Then the integral from a to b of f of x dx is going to be bounded on either side. So we can, looking at little m, well, this is just a rectangle. My length is a to b, and my width is little m. I know how to find the area of a rectangle. It's length times width. So my length is going to be b minus a, the distance between those 2 points, times my width of that rectangle, which is little m in this case. So we can see that it's going to be smaller than the integral because this little red area slash pink, purple area, because it's combined with the blue, is less than or smaller than the area under f of x. Then in the green, we can see that big M, that rectangle, is larger. It holds more than the area under the curve, which is the blue area. So that rectangle is going to be big M, b minus a. All right? Any constant, the integral of any constant is just going to be that constant times b minus a. All right? So the next one is also a pretty interesting one. It's called domination. In higher level mathematics, we also call this monoticity. So if you're looking elsewhere to kind of find more information on this property, and domination doesn't come up, monoticity might be the word to use. I don't know why the text uses domination. That sounds really creepy. So if f of x is greater than g of x on all a, b, then the integral of f of x is going to be greater than the integral of a, b of g of x dx. And we can kind of see that in our picture as well, right? That yellow area is a lot less than the big red area. So what if g of x actually just equals 0? Well, that means that the integral of a to b of 0 dx is going to be less than the integral of from a to b of f of x dx. Well, the integral of 0 is just 0. So this special case basically is saying that if f of x is a positive, basically on top of the x-axis, the entire interval, then that integral will also be positive. We'll talk about evaluating integrals next section. We have like a few fundamental theorems to kick out of the way first before we can do that. But this is kind of just applying properties before we get into like the meaty stuff. All right, so let's do a few exercises from what we know so far. So if the integral from -1 to 1 of f of x dx is 5, integral from 1 to 4 of f of x dx is -2, and the integral from -1 to 1 of h of x dx is 7, then what can we figure out from these three equations or expressions? So the integral from 4 to 1 of f of x dx, well, that is the order of integration flipped for this second integral right here. So I can write that as negative and then switch these guys. And then I'll get f of x dx, which is just -2. And that gives me 2. Pretty awesome. All right, well, the next one is a combination of the sum and difference and the coefficient one. So I can rewrite this as, 2 times the integral from -1 to 1 of f of x dx. So I'm distributing the dx to each term and pulling out the 2 and the 3. Kind of doing a lot of steps at once. Whee! So plus 3, negative 1 to 1 to h of x dx, all right? Well, then I have values for each of these integrals, so it's going to be 2 times 5 plus 3 times 7, what is that, 10 plus 21, so 31. Perfect. Now, I have the integral from negative 1 to 4 of f of x dx. Well, I can look up here, and I'm given from negative 1 to 1 and 1 to 4. So, additivity says I can take the integral from negative 1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx and make that equal to the left-hand side. All right, and we can plug what we know. So 5 minus 2 equals 3. Boom. All right, so if I have bounds on my integral, I'm going to get a number back out. If I don't have bounds on my integral, I'm going to get a function plus c back out. All right, so this is kind of something that we already talked about. If y equals f of x is a non-negative and integrable function over a closed interval ab, then the area under the curve y equals f of x, that's our curve, over ab is the integral of f from a to b. So the area equals the integral of f of x dx from a to b. Well, that says if f of x is a non-negative. Well, what if f is negative? Does it not equal the area? Like, what's happening? So the area between a and b and c are the, we're going to say that it's like mirrored basically, right? So from b to c, but that red area is just under the x-axis. So when we do Riemann sums, we made it so that the rectangle's height would be determined by the function value. Well, these function values are all positive, so that's why I get a positive area back out, right? Well, these function values are all negative. So delta x is always positive, unless we're going backwards. Remember, order of integration. But we're going forward here, so we're fine. And those function values are negative. So it's going to give me a negative area. All right. When I'm below the axis, x-axis, negative area. If I'm above the axis, positive area. All right. So we have another definition, and then this is the last thing we're going to do for this section. Quick section, but the next three are going to be pretty beefy. So we can define the average value of a function using the integral. So if f is integrable on AB, then its average value on AB is also called its mean. And we can write it as AB of f, and that's going to equal to 1 over b minus a times the integral from a to b of f of x dx. All right, so we're just going to multiply the area divided by the length of the interval, which is b minus a. So let's do an example of this real fast. If we find the average value of f of x equal to, we're trying to work. F of x equal to the square root of 4 minus x squared on negative 2 to 2. So the average value of f is going to equal 1 over 2 minus negative 2, the integral from negative 2 to 2 of 4 minus x squared dx. I had to think about that for a second. Which is going to equal 1/4 times this integral. I don't know anything about this integral. This does not look like any antiderivative rule we just learned. I'm frankly very scared of it. But I can look at the drawing that I have been so graciously given. And, well, that area looks like area of a semicircle. Right? Well, I know the area of a semicircle. That area is going to be 1/2 the area of a circle, which is pi r squared. Area of a semicircle, we'll call it SC. So this integral is going to be the area of a semicircle with radius of 2, right? To my center, we go here, that's 2. All right. So this is going to equal 1/4 times 1/2 times pi over 2 squared, which is my radius, right? So I replace the integral with something I know already. We're only doing this because we don't know how to take this integral quite yet. So 1/4 times, what is that? 4 pi over 2. And that's just going to equal pi over 2. All right? And that's going to be our average value of f. So we can draw that. I think pi over 2 is like right here. I could be totally wrong, but I know it's definitely more than 1.5. All right, pi over 2. And that's our average value. All right, so this section was kind of short, but it's going to be very useful when we move on to the rest of chapter 5, and definitely when we move on to the last 2 sections in chapter 6. All right, so I will see you guys tomorrow.